All right. Okay, so hi everyone. I'm really excited about this lecture today because today the two pieces of what we've been doing in this course come together. So in the first part of the course, we basically talked about, like Zoom, remember all the way back, search and planning and all of that. We basically talked about actions and utilities. What are the sequence of things I should do, actions I should take to maximize my expected utility, right? It was all about the maximization and the utility and all of that. For this recent third or so of the course, we've been talking about reasoning over uncertain variables. And today those things are going to come together. Because often when we have to decide what action to take, remember we're maximizing our expected utility, which means there are expectations. We need to reason about what's going to happen and with what probability so that we can make the rational or optimal decision. So today, this whole machinery of actions and utilities connects to the whole machinery of Bayes nets and graphical models and reasoning under uncertainty. So the first topic we're going to talk about today is what's called decision networks, which are a way of graphically connecting Bayes nets, which represented variables as nodes, with actions and utilities. And what this will open up is one step further is to start to think about information and learning information, observing evidence in a network, to start to think about that as something that itself has a utility. And we can finally formalize this very powerful and important notion of the value of information. Because when you get information, the saying, knowledge is power, well, information is utility. And today we're going to figure out how information and utility connect up in a formal way that's going to pull all of these threads together. So I'm excited. Let's talk about decision networks, okay? These are basically going to be taking these Bayes nets that we build and augmenting them with new kinds of nodes that represent utility and represent action. So here's an example of a decision network. Okay, in this decision network, we have the part at the bottom, which looks sort of like a Bayes net. So let's zoom in there. Let's look at this part at the bottom that looks like a Bayes net. This is a Bayes net. It has variables like what is the weather, and here that might be sunny or rainy. We're going to have super simple examples here so we can fit them on the slide. The weather could be sunny or rainy, and then there's going to be a forecast, which is another variable. And the forecast could say, we expect sun or we expect rain. And of course, the forecast isn't the weather, but it's a noisy indicator. When the true weather is going to rain, the forecast has some probability of actually forecasting it correctly, and there's another noisy forecast if it's sun, and that's all specified in the Bayes net. The Bayes net here is going to specify how likely each weather outcome is and how likely each forecast outcome is given the weather. All right, but this stuff up here is new, and in our running problem, there's going to be a choice. In addition to having weather, sunny or rainy, and a forecast sun or forecast rain, there's going to be a choice about whether or not to take your umbrella. And so this is a robot that has to make a choice. The choice is going to be take the umbrella or leave the umbrella at home. And then there's going to be an outcome, right? And over here you can see all the different ways the world can unfold. And so there's outcomes where it's sunny and you have the umbrella, and where it's rainy and you have the umbrella, and sunny and rainy when you don't have the umbrella. And we'll get into the exact details of our model of this robot, which is just going to be sort of a toy example of how the actions you take and the probabilities that you predict can interact. Okay? So let's go back and figure out what a decision network is all about. Remember, we've been talking about the principle of MEU, maximum expected utility. That means you should choose the action which maximizes your expected utility given your evidence. Right? And the more evidence you have, that's going to change the distribution of what you expect to happen. And so as you get evidence, the best action to take might change. All right, so let's operationalize this with these decision networks. The nodes that look like circles, ovals, those are going to be just like in Bayes nets, and the new nodes are going to have new semantics. So we have three kinds of node types. Actually, only the last two are actually new. These chance nodes they have the exact same semantics as in a Bayes net. A node represents a variable, and the name on the node says what variable it is, and it can be observed or it can be unobserved. If it's observed, that means we know which element of the domain of that variable is happening, and if it's unobserved, it's a random variable that we can compute distributions over. When you see these round nodes, you can think about them like chance nodes. Remember in Expectomax, we drew the nodes where the probabilities come in as circles? You can use that metaphor here too. One new kind of node is rectangles. So like here, the umbrella. Rectangles represent actions. So they're like random variables in the sense that they have a domain, right? And in this case, the actions for umbrella are take or leave. They're unlike chance nodes or random variables in your Bayes net in that there's not a probability distribution over them. You control them. Remember, you control your action, but you don't control the expectation over the world's response. That's the whole point of expect to max. You maximize over the actions, and then you live with the consequences probabilistically. So these rectangular nodes represent actions. You have to assign them. But that's good for you as an agent because you get to pick the best one. Okay, and the last one that pulls everything together are these diamonds, these utility nodes. And what a utility node is, it has parents. In general, its parents are going to include action nodes, right? Because your utility is going to depend on the action you take. And it's also going to include, the parents are going to include other random variables. Because usually the utility depends not only the action you take, but on the outcome of some variable that's in general out of your complete control. And so we'll construct distributions over. So in this case, the utility you get as a going outdoors and having fun robot depends on whether or not you take your umbrella, which you have control over, and whether or not it rains, which you don't. You don't have control over it, but of course you can reason over it. All right. So how can we use these networks? Well, first of all, I'm going to speak in general because to know exactly what the right thing to do is in a given network, we need to know all the details, right? We need to know what is the probability of rain, and if it's sunny, what's the probability that the forecast is going to say rain anyway? We also need to know details like what is the probability, what is the utility of taking your umbrella and then getting rained on? So let's jump ahead for a second and talk about the details, just so that we have this in our head. So remember, the new thing in this network is going to be the utility node. And the utility node, just like any other node in a Bayes net, it has parents. And it specifies something for each combination of values for the parents. So the utility node is going to specify something for each combination of take or leave umbrella and sun or rain weather. And the thing it's going to specify is the utility. So if we peek inside this decision network here and we have to look at the actual values, we've gotten rid of the forecast here. We might say, well, the weather has probability of being sun of 0.7 and probability of rain of 0.3. Okay, now I know not only that there is a random variable called weather, I understand the exact probabilities that I'm assuming govern it. Okay? Umbrella we know is take or leave. And in this diamond node, I have to have a list not of probabilities anymore, but of utilities. So I have to know what is the utility of leaving the umbrella at home and having a sunny day. And here that is 100 points, 100 utiles. That's the best possible outcome. You go and you play robot ball all day and have a great time. Now we have to look at the rest just so that we know this recurring example. So if you leave the umbrella at home and it's sunny, that's your best possible day of robot sports. If you leave the umbrella at home and it rains, that's your worst possible day. You get rained on, you rust, whatever it is not good. That's 0 utiles. What happens if you take your umbrella? Well, if you take your umbrella and it rains, you get 70 utiles. Imagine, it's not as good as that sunny day of playing ball, but you get to stand there happily dry. If you take your umbrella and it's sun, what's that? That means you see all these other robots happily playing robot soccer, but you are stuck dragging your umbrella around for no reason at all. That's pretty bad. It's not as bad as rusting, but it's 20. And so these have an order to them. The best possible case is leave the umbrella on a sunny day. The worst possible case is leave the umbrella on a rainy day, and the others are in between. Now you might say, well, that's sort of a weird set of utilities to give the robot, but remember that's what we do. We give the robot utilities, and with respect to those utilities, we compute optimal actions. If you have a robot that wants to rust as fast as possible, this would be a whole different table. Okay? So just like we come up with probabilities, and we'd like them to reflect something reasonable, but for this example, this is what they are. Okay? So let's go back here. What do we do with a decision network? Well, the main point of a Bayes net was we observe some nodes and we reason about probability distributions over others. Remember, we do a query of what's the probability of weather given this forecast. So Bayes nets, the whole point was to compute a posterior distribution over a node of interest given our evidence. Okay, that's what's going on down here. In a decision network, the whole point is to decide which action is best. So it's all really about picking an action. All right. So how does action selection work? How do you actually do reasoning in a in a decision network? Well, first of all, you have to instantiate your evidence, like maybe you know the forecast calls for rain. Secondly, you instantiate your actions because you control them. Okay, so you're going to have to say what action you're interested in. But unlike the evidence where, hey, it forecasts rain, you can't change that, the actions you can change. So you're going to instantiate the evidence the way it actually is, and you're going to instantiate the action nodes in every single way. Okay? That means the more actions available to you, the more times you're going to have to do this computation within the network. So you instantiate all your evidence the way it actually is. You instantiate your actions every single way. You compute the posterior distribution over all of the nodes that are relevant to the decision. Which ones are relevant to the decision? The ones that are relevant to the decision are the ones that are parents to the utility node. So if I want to know what is the best utility, what is the best decision, I need to consider all the different actions, and I need a distribution over weather so I can compute the expected utility of those actions. I don't know the expectation over weather until I do some computation in the Bayes net. All right, so we're going to have to compute an appropriate conditional probability. We'll see some examples. Once we have a conditional probability for all of the parents of the utility node, and we have all the different action instantiations, we can take each action and compute its expected utility given the evidence. And then once we've done that for each action, we can choose a maximizing one. So we'll see this in an example, but the basic flow here is you come to this network, and this network both tells you, here's my evidence, here's what that means for the variables that determine my utility. On the other hand, here are my actions, and here's what they mean for the utility. And now we can do expected utility computations and figure out which action is the maximizing one. Okay? Any questions before we do an example? Yep. The calculate posterior. The question was, can I explain? I'll show you some examples. How about that? That's a great question. It's, in fact, the perfect question, so thank you for leading into this next slide. So let's first do an example here, a very small example of a decision network. In this one, there won't be much calculating involved. So remember, weather in this example has 70% sun, 30% rain. We have the utilities where the best thing is you leave the umbrella at home and it's sunny, and the worst thing is you leave the umbrella at home and you rust in the rain, and everything else is somewhere in between. So now we can start to do computations in this network. For now, there's not actually going to be any Bayes net inference, okay? And that's because we're not going to have any evidence, and there's only one actual random variable here. But we do have an action here, which is take or leave the umbrella. And remember, we get to maximize over the action. So we're going to set it, but we're going to set it each way, and then we're going to pick one. So first, let's imagine that we set the umbrella node, which is an action node, to leave the umbrella at home. What are we going to do? We're going to compute our utility. How many points are we going to get if we leave the umbrella at home? Well, I leave it at home. That means we're either going to end up in this outcome or this outcome. I've left my umbrella at home. We're either going to get 100 or 0. Which one? Depends on something out of our control. It depends on the weather. So I can't compute my actual guaranteed utility. I can only compute an expected utility. I can say how many points am I going to get with the leave action averaged over the variables I don't control, which here is weather. So I do a computation, an expected utility computation for the action leave. Notice the notation here is important. It's the expected utility of an action. Okay, actions have expected utilities. Well, that's just the utility of the action for the outcome for weather averaged over the likelihood of that outcome. So we could do the math, and so we'd say, well, sometimes we get 100 points. That's when it's sunny. 70% of the time that happens. Okay, so here is the utility for leave, sun, times the probability that outcome actually occurs. Now, sometimes we get 0 points. And when we get 0 points, that's because we've left the umbrella at home, but it's rained, and now we're here rusting in the rain. How often does this happen? 0.3. Okay, so we take this average. That gives us an expected utility of 70. Is that good? I don't know, right? It's just it's all with respect to the other actions and the other expected utilities we have available to us. But the expected utility of the action leave involves averaging over the other parent of u, which is the weather. So we can do the same expected utility computation for the other action. We can say, you know what? Let's imagine instead that I take my umbrella. All right, well, if I take my umbrella, I can now compute the expected utility of take. This is again an average of actual utilities, except now we're averaging these utilities on the bottom. It's either going to be take my umbrella and I get rained on, or take my umbrella and it's sunny. So I can pull the numbers out of the network and I can compute the average. It's still 70% chance of sun, except now we only get 20 points when that happens. 30% chance of rain, we get 70 points when that happens. And now the expected utility we will get under this weather distribution for taking my umbrella is only 35. So there's expected utility for leave and there's expected utility for take. I get to pick amongst them. What should I do? Okay. I should leave my umbrella and score my 70 points instead of taking it and being stuck with an average of 35. Okay? So the optimal decision here in this network is leave. Okay? And this computation we used to get to that didn't really have much of anything to do with a Bayes-net. In fact, it was just really a tiny little expect-to-max computation. But hopefully by now this kind of computation feels very, very familiar from the early part of the course. Okay? Everybody follow the flow here. We check what's my expected utility for leave, what's my expected utility for take, and then I pick an action. That is action selection in a decision network. Okay? Now this decision network was trivial. It was trivial in the sense that the probability I needed to compute my expected utility, remember, was the distribution over weather, and it was sitting right there in the network because this Bayes-net is small and trivial. Okay? All right. So the optimal decision is to choose the action leave. That corresponds to an expected utility of 70 from this computation up here. And we write the following. Okay, so this is important because this is maybe a little bit different than the notation you're used to. We write the maximum expected utility, MEU. Maximum expected utility is the maximum over all the actions of the expected utility of that action. So think expect-to-max. It's a maximum over actions, and then it's an expectation over outcomes. But here's the new part. The argument to an expected utility was an action. It's the expected utility of an action. The argument to the MEU here is my knowledge. It's my evidence. Because the right action is going to depend on the evidence I have. And as I get new evidence, I might choose different actions. Right? Maybe if there was a forecast for rain, maybe my actions would be different. My expected utilities would be different. My MEU would be different. So I write the MEU given no evidence, that's that empty set there, is 70. Okay? All right. We can take that computation, and in a second we're going to see that connect up to a Bayes-net style query and a graphical model. For now, let's unfold what I said in words and wrote in equations into a tree and see if we recognize the tree. Okay? So, there's the tree. Okay. How does this work? We say, really, even though somebody's drawn me this funny decision diagram, really, I have an expect-to-max problem. My problem is, I'm an agent with a choice. So I have a max node. I'm going to choose either the take or leave action. So remember, in expect-to-max, we have a max over actions. I can choose take, I can choose leave. Remember also that max nodes represent states. What is the state here? Well, here the state is my knowledge. And here my knowledge is nothing. I don't know anything about the weather. I don't know anything about a forecast. So the set of evidence I have here is the empty set. So from the state where I have the empty set of evidence, I have two actions, right? So this is the actions. I could think of this as the state if I wanted to use my old terminology. The state is I have no evidence. The action is I can take or leave the umbrella. The chance nodes here represent what the weather will do, and the probabilities that govern them are the conditional probability of the random variable weather, given my evidence, which here is empty. Okay? And so here would be all of my outcomes. These are governed by the probabilities from the Bayes-net. And then the game ends and I get a utility. Right? So the outcomes are either sun or rain, and then there's a utility. And the utilities are given by that utility nodes table. This is just like an expect-to-max or a tiny little MDP. There's one thing that's very important that's different. The thing that's different is when we did expect-to-max on, some game or something like that earlier in the course, remember we assumed that the probability fairy came and said, this node, you're rolling dice, even chance. Or this node, here's the probability that governs the outcomes. Here, when we say, what is the probability of weather given the forecast, we actually have to do computation to figure out the probabilities from that expectation node. How do we do that? We're going to do that by running Bayes net inference. Okay? But that's the main thing that's changed, is now we have to do computation at each node to compute the probability of the outcomes given our evidence. There's also been a little bit of a shift in perspective, which is that once we get into these decision-making problems, the state is usually the set of things we know. And we'll see more of that today. All right. We're going to do an example where some Bayes net inference is required. Any questions before we do that? Okay. So here, again, we're going to make the same decision. I'm a robot. I wake up in the morning. I want to know whether to take my umbrella or not. I have basically the same utilities. I have the same action node where I can choose to leave the umbrella or take the umbrella. The only thing that's different is now I'm actually going to listen to the weather forecast before making my decision. That's intuitively probably a good thing, right? Because if you listen to the weather forecast, you have more information. Information is power, and here that means information is utilities. Okay, so we do the same computations now. We say, well, I can leave the umbrella or I can take it. That's that top branch of the expect-a-max where I have a max node with different actions underneath it. So I take it or I leave it. Let's do the computation where I leave the umbrella. It's going to unfold the same way. If I leave the umbrella, I'm either going to get 100 points or I'm going to get 0 points. What's different is the probability of 100 versus 0 is different now because I've listened to the forecast, and let's imagine I now have the evidence forecast equals bad. Now, I also need to tell you what's the probability of the forecast being good or bad given the weather, but here we've shortcut it a little bit, and I'm just going to spot you the information that in my Bayes net, conditioned on the evidence that the forecast is bad, rain is now 2/3 and sun is 1/3. Okay? Stare at this really closely. This thing I've given you for this slide, the probability of the weather given the forecast, is not the probability from the Bayes net. The Bayes net tells you P of W and P of F given W. This is P of W given F. I can compute that. I can compute that with variable elimination, or in this case, just Bayes rule would do it. Okay, but let's go through let's imagine that I've pre-computed that quantity for you. So I know the forecast is bad, and now instead of a 70% chance of sun, there's a 34% chance of sun. So I can do that same computation. What is the expected utility of leave? Well, now I'm computing the expected utility of leave given information, given that the forecast is bad. It's those same utilities, 100 and 0, but now the probability of sun versus rain has changed. So when I unroll that expectation, it's got the same terms, but the weights are different because I have new evidence, and that means my distribution over weather given my evidence has changed. So now the expected utility of the action leave given the evidence forecast equals bad is now 34. I can do the same thing for take. What's the expected utility of the action take given the forecast is bad? Well, again, it's either going to be 20 or 70, so I have to average those together. This utility is the 20 and 70. These probabilities are the likelihood of sun versus rain given my evidence. So I unroll that computation again. It's the same 20 and 70, and now I compute my average and I get 53. Okay. Same actions, same outcomes, different weights. Now which one is the maximizing action? I look at this. In general, the numbers are lower because my evidence is bad. This is a bad day. Days where the weather forecast is bad, on average, are worse. So notice my utilities dropped. But which one is the maximizing utility has changed. Now the maximizing action is the take action. I should take my umbrella. Okay? So the optimal decision is take, and I write the following. Make sure this notation is clear. I write the maximum expected utility. That is the expected utility under optimal action selection when the forecast is bad is 53. Which action leads to that MEU is the action take. Okay? This MEU is the expect-a-max value, and the argument to the MEU is my knowledge state. My knowledge state here is I know there's a bad forecast. Before, my knowledge state was empty. I didn't know any variables. Okay? All right, so we ran through this decision network once when we didn't have any evidence, once for forecast equals bad. We could go through it again, and I invite you to try. We could go through it again for forecast equals good. In order to do that, we'd actually have to look and see the exact distribution of forecast given weather. Okay. All right, let's look at that expect-a-max tree again. It was the same form of computation as before I had evidence. So I had a state, right? I had a state, and here my state is, I know that the forecast equals bad. So my state, which is my list of observed variables, is different. I have the same actions, so I have the same actions, take or leave. I have the same outcomes, sun or rain, from my chance nodes, except now the probability that governs sun versus rain is the probability of that variable, weather, given my evidence. So now the probability is instead of 0.7, 0.3, it's 0.34, 0.66. Okay, but the structure of the computation is very similar. Okay, different knowledge state. Any questions before we see an example of this in Ghostbusters? All right, so let's first just see Ghostbusters happening, and then all right, let's remember the Ghostbusters game. So in this version of Ghostbusters, so far you've only seen the case where there's one ghost. We'll see some cases with more ghosts starting next week. Okay, so there's one ghost in there somewhere. Right now we have no evidence of where the ghost is, and so you're seeing a conditional probability represented as numbers in a grid. Okay, so each of those squares has probability 0.02 of being where the ghost is. Now, I can take sensing actions. When I take sensing actions, I move from my current knowledge state, which is I don't know anything. I know the model, but I don't know any random variables values. But I can figure out what is the value of the sensor reading in the upper left corner. Boom. I'm now in the knowledge state. Sensor reading in the upper left is green. In that state, I have a different posterior distribution over the variable of interest, which is where's that ghost. And I can gather more evidence. Stab at my... Okay. So, given all of these sensor readings, what you can see here is the posterior distribution over the variable, where is the ghost position variable. And here, the most likely single spot has probability 0.77. Now, I can bust. I'm going to bust at that 0.77 square. Am I going to hit the ghost? Maybe. What's the chance I'm going to hit the ghost? 0.77. Let's roll the dice. We got it. Okay. So, 100 times I give this lecture, 77% of the time we end up here. The rest of the time, ghost is somewhere else. Okay, so remember Ghostbusters. We're going to see Ghostbusters a whole bunch over the next few lectures. Let's see that as a decision network. Well, first, there's sort of the top part. The top part says I can bust, and the bust action has some large number of actions. You could actually take a step back and say, wait a minute, instead of busting, couldn't you sense? Couldn't you do another probe? Yes, we'll get to that. For now, let's just imagine it's time to bust. Bust now is an action where there's a value of that action for each square on the board. What's my utility? Well, the utility depends on whether or not the ghost is actually in the location I bust. So in order to tell you the utility, I need to know where did you bust and where was that ghost. So this top part represents the utilities, the actions you select, and the expectation that governs the outcomes for each action. What about all the rest of the stuff? What about all the sensors and so on? Well, you could imagine there being the whole rest of the Bayes net sort of from here down, which has a variable for each sensor reading, most of which I don't have, so they're unobserved, and a couple of which, remember I did a reading in the upper left, and then I did a reading over here, and then I did a reading over here, and there's a couple of these that are filled in. Conditioned on that evidence, I can compute the distribution over ghost location given the evidence, and then I can go through the computation at the top, which is actually pretty simple. It boils down to bust in the most likely location. Okay? So that's Ghostbusters as a decision network. We'll come back to the case where one of the actions you can take is to get more evidence by revealing a sensor. Right? And that's actually an important case, because that's the case where what you get for your action isn't a utility, it's more knowledge, which in turn has expected utility associated with it. So we need a little more machinery before we can do that. All right, we're going to not do that. Any questions from that before we start getting into exactly that issue of value of information, which is the question of how many utility points is it worth if I reveal this variable to you? Okay. All right. Value of information. I also think this is really cool because this is the kind of concept that shows up, once you're sort of aware of it, it shows up every day in your thinking about the world, right? I can take actions. Of course I can take actions. Many of the actions I take are gathering information. I gather information so I can make other decisions well, and so that information itself has utility. Today we're going to talk about the value of information, which is in terms of utility, right? Because as I change my evidence, my MEUs go up and down, and so I can talk in a meaningful way about change in utility. So here's the idea. We're going to take a decision network, which is going to have a BayesNet part, which connects all kinds of variables together, including ones that we don't yet know, and that connects them up to utility variables. So we've already seen that in the first part of this lecture. What we're going to do is we're going to use these networks to compute the value of acquiring evidence, and we're going to do that directly in the decision network. What's that mean? Well, remember, if I put a decision network in front of you and say, all right, decision time, are you taking the umbrella or not? You can say, okay, hold on a second, calculate, calculate, calculate. I'm going to take the umbrella, and my MEU is going to be 34. Okay? We can then talk hypothetically about what would happen if I showed you a variable. Right? You'd make better decisions. When you make better decisions, you get higher utilities. And so we can compute, on average, does your utility go up when I show you a variable? How much does it go up? And there's a whole bunch of different quantities we have to reason over in order to make that precise. But we can do that directly from the decision network. So here is a simple example. This example, I think, is really good at one thing, which is it's really good at focusing in on how value of information works and how evidence variables are sort of connected in a deep way to utility. What's not good about this example is it's such a small example and there's symmetries in it. So you're going to look at this and think, wait, what does this have to do with Bayes nets? Because the numbers are all small enough you can sort of do them in your head from first principles. So we'll see other examples that are a little less small and symmetric as well. All right, so we're going to compute the value of acquiring evidence. And let's imagine that we're going to drill for oil or substitute any isomorphic problem here. Here is a toy decision network here which has 3 variables in it. The variables are the oil location. So that's your random variable. The oil location is either going to be in lot A or lot B. So we can imagine here is, let's put A over here. Here's B, right? We can either drill in lot A or drill in lot B. And let's imagine that exactly one of them has oil. So oil location either takes on value A or B, but I don't know which. And it's 50-50. Drill location also is A or B, right? I can control which. I can pick to drill A or to drill B. And then there's a utility node, okay? So there are 2 blocks, A and B. Exactly one has oil, and that oil is worth K in terms of utility. So utility says that if you drill where the oil is, you're going to get K. If you drill where the oil is not, you're going to get 0. Okay, you can drill in one location. The prior probabilities are 50-50. They're mutually exclusive. And here's all the numbers. Oil, A or B, 50-50. Drill location is A or B, but you get to choose, so there's no probabilities on that. And then if you drill and the oil are in A, or you drill and the oil are in B, you get K. Otherwise, you get those zeros. Okay? That's the setting. Now let's talk about how well you're going to do. Well, if I drill in A or I drill in B, it's a symmetric problem. And I get to pick. But if I drill in A, what's the expected utility of drilling in A? Well, half the time I get the prize, and it's K, and half the time I don't get the prize, and it's 0. So my expected utility of picking A is K over 2. My expected utility of picking B is also K over 2. Okay, so the MEU here, the maximum expected utility, for the state where I don't know any of the variables' values, is K over 2, and it's achieved by either drilling in A or drilling in B. Okay? That's the baseline. The question is this: what is the value of information of this variable O, the oil location variable? Okay, so we're posing a question about a random variable that is not currently observed. And I'm saying, what is the value to you if I reveal this variable to you? So in this case, informally, that's the value of knowing where the oil is. Okay? Well, how should we think about the value? Well, this is a utility computation. So all values are in terms of utilities, and in particular, expected utilities. And so we can look at the gain in MEU from the new information that's revealed to me. It's going to turn out to be an expected gain. This is the part that's a little bit confusing. We'll work through this a couple times for a couple different examples. But we're going to compute how much better we do in an MEU sense if I reveal this variable to you. So it goes something like this. Let's say I can do a survey. The survey is not another, for right now, the survey isn't going to be another node in my network. The survey is just sort of language I'm using for reveal the value of oil location to you. So imagine it's a perfect survey here. Okay, the survey can say the oil's in A or the oil's in B. Now, I don't actually know what's going to happen. So when I talk about revealing oil location to you, I'm not talking about revealing to you that it's in A. I'm talking about revealing to you where it is, wherever it is. So when I reveal a variable, it's wrapped up in think about like value of information. If I give you a variable, it's a little present, and you unwrap it, and what's inside you don't know, right? It could be any value of that variable. And so you need to think about the uncertainty over that as well. All right. So if I do this survey and it tells me where the oil is, now suddenly I'm in a different decision network. I'm in this decision network. I'm in the decision network where oil location is revealed to me. Well, what am I going to do? Well, I can drill where the oil is, or I can drill in the other place. What should I do? I should drill where the oil is. How well am I going to do? On average, K. So before I reveal this variable to you, you were going to get K over 2. After I reveal the variable to you, regardless of which way it falls, you're going to get K. So your gain in MEU is K over 2. We write this as the value of information, VPI. Say YP, I'll be back to that in a second. The VPI, or the value of information for the variable oil location, given no other evidence, is K over 2. That is the difference between the MEU of taking your best action without the variable and the MEU of taking your best action with the variable. Okay? Another way to say this is the fair price of information about that variable should be K over 2, assuming you're paying in utilities. Okay. Let's take our break now, and then we'll do another example of value of information in a case where it's not sort of small and symmetric and every outcome does the same thing. So we'll take a couple-minute break now, and then do more value of information. Okay. All right, let's get started again. So we're talking about value of information computations. And we're going to go back to the weather and umbrella example where I'm a robot and I have to decide whether to take my umbrella with me or leave it at home. And the utility of that depends on how the weather actually turns out. Now, we already computed earlier in this lecture how well I'm going to do if I act optimally in the absence of any evidence about the weather. And the answer there was there's a 70% chance of sun, and if you work out the various utilities and their various expectations, the best thing to do was to leave your umbrella at home, and the expected utility of that action was 70. So the MEU, that is your utility under optimal decision making, when you have no evidence of any variables, was 70. The MEU was 70, and it corresponded to leaving the umbrella at home. Now, the question is, if I am a robot and I would like to have a good day and not rust in the rain, and I don't want to needlessly take my umbrella with me, I have the option of listening to the weather forecast. And so I can ask the question, how much value does that have? That means how much, if at all, will my utility go up if I reveal the forecast variable, which I can do by, say, turning on the radio? Well, I don't know. I know my MEU is 70 if I take my best action, which was to leave the umbrella, in the absence of any evidence. Now, I can do another computation, which we also already did, which is, what's my MEU when the forecast says bad weather? And remember, we computed that all out. It turned out the MEU was lower. It was only 53, because this is a bad day. The MEU was 53, and it corresponded to the action, or it was backed by the action, taking my umbrella. So remember, when I listen to the forecast, it's possible it'll say, sorry, bad weather. But it's possible it'll say, weather looks good today. So I also need to do a computation to see what my MEU is if the forecast is good. And we didn't do that, but if you kind of write that down and you kind of plug and chug through, you end up with another MEU, which in this case is 95. This is a good day, so this one is better than 70. And here the MEU is 95. It's backed by the decision to leave my umbrella at home. And usually it's sunny when you see a good forecast. And so the MEU ends up 95. So now we have to talk about how much is it worth to you if I reveal from this initial state where you have no evidence, if I reveal the forecast to you. And so you look at it and you're like, well, that sort of depends on what the forecast is. If the forecast is bad weather, your MEU is going to drop. If the forecast is good weather, your MEU is going to rise. But the thing is, when I offer to tell you the forecast, I'm not offering to make the forecast good or to make it bad. I'm offering to unwrap the present, and you get to see what's inside. And so to figure out how much on average my MEU is going to go up from 70, I need to reason about how likely it is that I'm going to have a good forecast versus a bad forecast. So what's the quantity I need? In order to compute the gain here, I need to compute the probability of a good forecast versus a bad forecast, given my other evidence, which here is nothing. Okay? So what is that? That's the forecast distribution. That's the probability of this forecast variable given my evidence, with no other evidence. And so I could compute that. It's not sitting in the Bayes net. P of W is sitting in the Bayes net, right? In the weather node is P of W, and in the forecast node is P of F given W. In this case, I want P of F, because that will tell me when I get the forecast revealed to me, how likely is it to be good versus bad? Well, if I plug and chug in my Bayes net, it'll turn out that the marginal probability of a good forecast is 59%, and a bad forecast is 0.41%. You need to know the probabilities in the Bayes net to compute this. All right, so now what can I do? I know my MEU with no evidence. I know my MEU with a bad forecast. I know my MEU with a good forecast. So when I come to you and I say, how would you like me to reveal the forecast? You can say, well, let's figure out how much my MEU goes up. Well, 59% of the time, you're going to tell me the forecast is good and I'm going to get 95 points because when I make my optimal decision, I'm going to leave the umbrella at home. But 41% of the time, you're going to tell me the forecast is bad. I'm going to take my umbrella and I'm going to get my 53 points. This part here the sort of weighted outcome of what will happen when you reveal the variable to me and then I make best possible decisions afterwards, that's that expectation. This term here, 70, that is what will happen if you don't reveal the variable to me and I just make my best decision about an action in the absence of evidence. So that difference is the value of information. So I can plug and chug on that, and I get 7.8. What does that mean? That means that from an MEU of 70 with no evidence, if you say, hey, I'll reveal the forecast to you, you say, great, that's worth 7.8 utilities to me. Does that make sense? I've got my MEU without the evidence. I've got my MEU with the evidence. But my MEU with the evidence has to be an average of the different values which will be revealed to me when I open up the package. Okay? We can write this as follows. And at this point, remember there was this point with Bellman equations where there are just like a bunch of variations of the same kinds of equations. This is that point with VPI computations. Here, let me change colors. Here we have the maximum expected utility given my current evidence, which in this example is empty. Okay, but there's the maximum expected utility of my current evidence. And I want to compute what is the value of learning information about E prime, meaning I'm going to reveal E prime, it's a variable, I'm going to reveal it to you, on top of your existing evidence E. Well, right now you can achieve an MEU of whatever it is given evidence E. You do your computations, you pick your best action. I'm offering on top of that to reveal E prime to you. When I do that, you will get new MEUs. Your new MEUs will be optimal scores when you have evidence E and the new evidence E prime that I've just revealed to you. Sometimes they'll be higher because you like E prime, and sometimes they'll be lower because E prime is unfortunate. Now, you don't know which outcome you're going to get, but you can compute a distribution of what's inside the package E prime. That is the probability of the particular values E prime given the evidence E you already know. So this is a predictive probability. What is the probability of this unknown variable that I'm threatening to reveal to you, given all the evidence that you already have? When I take that expectation, this is an expected maximum expected utility that represents, on average, after I reveal this unknown quantity to you, how many points will you get acting optimally? We can compare that to what I would do now. So this is then. Now I would get MEU of little e. Then I will get an average of MEU E prime. That difference is the value of information of E prime given E. All right. Any questions before we do some properties of value of information? Yep.
Will the value of information always be 0 or greater?
Question was, will the value always be non-negative? Yes. It will be. And that's coming very, very soon. It's a great question. Now, the actual outcomes, remember, can be positive or negative, right? Because if I reveal to you that the forecast is bad, you will actually compute a lower MEU than if I hadn't revealed the variable to you. But that variable might have been good, and there's balanced off by a case where the MEU goes up. And that expectation is always going to be non-negative, and we'll see why in a second. All right, so here's the value of information. Let me walk through the definition in equations first, and then we'll talk about its properties. So we assume we have evidence that capital E, which may be multiple variables, takes on value lowercase e. If we act now, we achieve MEU of little e. That is, we maximize over actions A, we average over outcomes S, and we take a distribution over utilities. Standard expect to max. Let's imagine that we discover that when we unwrap E prime, it takes on value little e. If we act then, we will achieve MEU not of just E, but of E comma E prime. That means it's still going to be a max over actions. It's still going to be an average over utilities, except now we're going to be, instead of making our decision based on evidence E, the probabilities will be informed by E prime as well. So that distribution over states S will be different. So we might make a different decision. When we max over A here and when we max over A here, we might make a different decision. We might suddenly take our umbrella with us because we heard a bad forecast. All right. If we act now, we get MEU of E. If we act then, we get MEU of E comma E prime. But E prime is a random variable whose value is unknown. I am not offering to make the forecast good or forecast bad. I'm offering to reveal it to you. So we need to have a prediction about what E prime will be in order to compute how valuable that information is to us. So the expected value, if E prime is revealed and then we act, regardless of what it is, we're going to do a different a computation. That is the MEU. That's the utility we will achieve on average, acting optimally, when we know E and have E prime revealed to us. That's why it's still a capital. That's going to be this distribution over possible lowercase e primes that we'll see of the MEU of what we would do upon seeing lower e prime. The value of information is the change. The value of the information is how much the MEU goes up by revealing e prime and then acting, as opposed to acting now. Okay. So let's talk about some mathematical properties, which I think are easier to see, maybe thinking about this from sort of an expectamax state. So first, let's look at the expectamax tree for MEU of just acting right now. We're in some state. The state we're in here, bad choice. So this is now. Let's just call this E. Okay, we're into the state where we know E. We have actions A available to us. And then the outcome we predict is underneath we do inference over S, which is whatever the parent of the utility is. Given our evidence E, that's our computation. We think about augmenting our state and therefore our evidence and therefore these probability computations with another piece of evidence. We get a computation that looks the same. But of course, this here is this and this. Because what I'm not really offering to do is I'm not offering to give you E prime plus E prime or minus E prime. I'm offering to give you, so kind of put you into a chance state. I'm offering to put you into a state where E prime will be revealed to you. And the first thing that's going to happen, the first branch here is, well, what is it? You tell me the forecast. Is it good? Is it bad? That's the first branch. And it has a probability associated with it. And that's this predictive probability we talked about. Okay. This piece here, what the heck is this chance node on the top? Why is it? That represents the revealing of the information. And I think that's the part that's hardest to sort of to get the details on. All right, so here's some properties. All these properties can be derived either from the equations or from kind of thinking about expectamax quantities on the different trees that they correspond to. So here's some properties. First property is non-negativity. So whatever evidence you have, if I walk up to you and say, here's a random variable you don't know, what's the value to you? Well, that value might be 0. But it's not going to be negative. Next property, it's not additive. So if I walk up to you and say, okay, you've got evidence E, but here I have 2 variables that I could reveal to you. And I say, well, what's the value of revealing this variable? So you do some computation, you're like 7.3 utiles. How about this variable? You do some computation, you're like, that one's 4.2 utiles. If I observe both variables, you don't get to add the VPIs. So if I offer to reveal A and B, the value of that to you is not the value of A plus the value of B. Why? An easy way to see that is, let's say, actually in your probabilistic model, A and B are basically the same variable. What if I offer to reveal the weather forecast and the weather? Well, they're both very useful to you, but they're basically the same thing. And so once you've observed one, the other one's a whole lot less useful. So VPI is non-negative, but it's also not additive. It is, however, order independent. So if I have A and B and I offer to reveal them to you, if I reveal A and then B, or B and then A, you end up in the same situation. So it shouldn't be too surprising that if you compute the value of information sequentially, what's the value of revealing B, and then once I've revealed A, add to that what's the value of revealing A, you get the same regardless of which order you do. All right, let's ask some questions about VPI. Here's a quiz. You're in the cafeteria. There's a soup. The soup of the day is unknown. It's a mystery soup. They haven't opened the lid yet. It's either clam chowder or split pea. Okay, so it's a random variable here. But you're not going to order either one. What is the value of being told which soup it is? Big value, little value, zero value. Who says big value? Who says little value? Who says zero value? Okay, zero wins. Why is this, right? Why is it that finding out this variable, right, you have knowledge, right? But it doesn't change your utility because it's not going to change your action, and any evidence that does not change your action, regardless of the outcome of that random variable's reveal, is going to have value of information 0. Information only has value if there is some outcome that can be revealed to you that will change your action. Okay? All right. So in this case, the value of information is 0 because it doesn't affect your decision. You're at a picnic. There are 2 kinds of plastic forks, slightly different. One of them is slightly sturdier, but we're not sure exactly which one. I offered to reveal to you which is the slightly sturdier fork, so that you can choose a fork in a more informed way. Is this information highly valuable, slightly valuable, or 0? Who says highly valuable? Slightly valuable. 0. Okay. In this case, let's first check, is this information going to change my decision? It might, right? I might as well take the sturdier fork because, why not? It's slightly better to have a sturdier fork. So here's a case where the value of information is probably not 0 because having that evidence will change my decision. However, the utilities involved are all pretty much tied. So it's probably not going to make a big difference to my utility not because it won't change my decision, right? This evidence may be extremely likely to change my decision, but the utilities involved are all very close. So the value of information will be low. Okay, we're playing the lottery. The prize, will be 0 or $100, and you can play any number between 1 and 100. They're all equally likely to win. So the random variable is what will be the winning number. Your action is which number would you like to play? What ticket would you like to buy? What is the value of information of knowing the winning number? So I'm going to reveal to you the number before you act rather than after. High value, low value, 0 value. Who says high value? I guess this is, okay. 100 million. All right, so high value. Well, let's think about what it is. Right now, if I play the lottery, what am I going to get? I'm going to get an expected utility of $1. So let's pretend my dollars are my utility here, which for small numbers might be reasonable. Okay, so my expected outcome here is going to be $1. If you reveal this information to me, regardless of what you reveal to me, I'm going to become incredibly good at this lottery and I'm going to get $100. So on average, I'm going to get $100 if you reveal the evidence to me. And if you don't reveal the evidence to me and I just have to play without that evidence, I'm going to get $1. So the gain here should be 99 million, or 100 million minus 1. You say, what about the cost of the ticket in the first place? That's separate. That's just a cost against the utility regardless of what happens. Okay. I've been saying value of information, but I've been writing VPI. That's because classically this thing is called value of perfect information. What if somebody offers you some imperfect, slightly decayed information? Okay. People used to worry about this, but it's really simple for us, which is that in our formulation, there is no imperfect information. All information is perfect. What is information? Information is revealing the value of a random variable in your network. That's it. You either know the value of the random variable or you don't. Right? It's evidence or it's unobserved. What was the point of imperfect information? People used to think about things like, I'm not going to reveal to you the weather. I'm going to reveal to you a forecast of the weather, which is sort of a noisy form of that variable. The way we formulated things, revealing the weather forecast is not an imperfect reveal of the weather. It is a perfect reveal of the weather forecast, which is itself connected to weather in some probabilistic way. And so what we've done is we've taken any noisy variables that you might have, put them in as new variables in the network, and offered to completely reveal this variable to you, which may or may not actually be useful in your computation, but that variable itself is either revealed or unrevealed. So that's where the imperfect information went. It's gone. Let's look at another example. Back to drilling. Remember, this is the case where you can have oil in A or B. You can drill in A or B, and you get K if you find the oil, and you get 0 if you don't find the oil. In this version, your MEU without evidence was K over 2, because half the time you get the oil. And your MEU with the evidence is always K, and so the value of information here was K over 2 for revealing the location of the oil. Okay, so that was the VPI of revealing oil location. It was K over 2. We did that before. Let's add to our network. Let's add a scouting report. What's a scouting report? A scouting report is you send this red robot out to do a probe in a location, and it says, I found this kind of rock in the core sample, and I think this is the probability, therefore you can compute of the oil. So it doesn't actually tell you whether the oil is there, but it gives you some strong evidence of whether or not the location that you scouted has oil. Okay? So what is the value of information? So forget it. You don't know oil location. I offered to give you the scouting report. Should that have value to you? Will it change? One check is, will it change where you drill? If the scout says, I think I found oil in A, yeah, it'll change where you drill. You could be wrong, right? You probably would want to know the details of the probability here. In fact, you probably want to make sure it's not like a reversed scout, but even that has positive value. So this has value of information that is going to be non-negative. However, this one was K over 2. The value of the scouting report, is it 0, between 0 and K over 2, or more than K over 2? So who thinks it's 0? Value of scouting report is 0. Who thinks it is still K over 2? More than K over 2? Less than K over 2, but still greater than 0. All right, that seems like the majority one. That's right. So here, this is still going to have value, and intuitively that makes sense because it doesn't tell you where the oil is, but it gives you some information to that, and you could do the computation and figure out, based on the actual numbers, exactly what the gain in information or in utility here is on average. Okay, so it's probably sort of between 0 and K over 2. It's sort of somewhere in the middle. All right, let's add another variable. So let's say the scout report of, I found signs of oil in lot A. Let's say there are different scouts, right? There's the good scouts that are like, do a really thorough core sample. And I know actually nothing about the geology here, but there's a really good scout and a really bad scout. And this random variable is which scout got sent out to give you that report. What is the value of knowing, we don't know oil location, we don't know scouting report. I'm only offering to tell you whether or not I sent the good scout or the bad scout out. Value of information. 0, between 0 and K over 2 or more. Who says 0? Okay, 0. It's not valuable. But why? I just told you it was a really good scout. Why is it not valuable? Well, intuitively it's not valuable because who cares how good the scout is? You didn't tell me what it found, right? But let's think about this in terms of the graphical model. I've offered to reveal to you the scout variable. What are you going to do with that information? All you do in order to make a decision about drill location is compute the probability of oil location given your evidence. So without any evidence, you would have said, all right, I'm going to compute P of oil lock, and then I'm going to make my decision. And now you say, all right, well, you're going to tell me scout, and what am I going to do with that information? I'm going to compute P of oil lock given, I don't know, that it was scout 1. What is that? Well, let's eyeball this Bayes net and run d-separation in our head. One thing I can do looking at this network is I can conclude that the oil location variable and the scout variable are conditionally independent in the absence of other evidence. So they're marginally independent here. And that means the probability of oil location is the same regardless of whether or not I tell you what the scout is. And if I give you evidence, right, I could plug and chug in this network and actually compute this, but if I give you evidence that is conditionally independent of the variable of interest given your other evidence, it's not going to change the computation that goes into the MEU, and therefore it's not going to change your actions, and therefore it's not going to change the actual MEUs, and it's not going to, and so that's going to have value of 0. However, let's say you already know the scouting report. So I've told you scouting report says, oil likely in A. And now I offer, hey, that report you have, I'll tell you whether or not it was the terrible scout that gave it to you. Does this have value now? This feels like it should have value. So this shows up in exactly the same way under a deseparation computation or a conditional independence analysis here, that oil location and the scout quality are marginally independent. So discovering scout doesn't help me. But if I know scout report, conditioned on scout report, scout and oil location are no longer conditionally independent. And therefore, there may be some value associated to that. The general property here is that if the parents of your utility node are conditionally independent of the variable I'm offering to show you, then it has value of information 0, given your current evidence. Okay. All right, and that should feel, it makes intuitive sense, and it should make sense from a deseparation analysis as well. Questions? Okay. Let's quickly talk about POMDPs. What are POMDPs? They're partially observable Markov decision processes. What are these? Remember, Markov decision processes or Markov decision problems were like non-deterministic search. I was in a state. I knew what state I was in. I took an action, and I knew what actions were available to me. And the thing I didn't know is what state I would end up in. So the thing that was non-deterministic or uncertain was the outcome of taking action A in state S. In a POMDP, I take that one step further, and I say not only am I not sure what my actions will do, because they have multiple outcomes, I'm also not sure what state I'm actually in. What could that mean? This is actually, life is a POMDP, right? You're a robot and you're like moving around and you have actions like drive left, drive right, but you're not really even entirely sure where you are. You may have a belief distribution over where you are, but in general, you don't even know the state of the world for sure. The only thing you really know is your observations over that state. So POMDPs are designed for this, and we'll see them a few times in this course. But for now, let's take a first cut at them. A Markov decision process was, remember, states. You're in a state. You have actions available to you. There's a transition function which encapsulates the uncertainty over what will happen. Now, if you stare at this, you think, actually, this probability distribution over the outcome, given some evidence, we have better tools for computing that now. So you can imagine MDPs that have little Bayes nets living in their transition functions. But let's set that aside for now. A POMDP adds something new. It adds observations O and an observation function. So now, instead of actually knowing what state S you're in, all you're going to know is what states are possible and what observations you've made. So instead of a robot knowing it's in a square in a grid world, you might just have laser readings from all the different angles around you, and that lets you compute or track where you believe you are. We'll get into this with tracking problems with hidden Markov models starting next lecture. Okay. So what's a POMDP? Well, one way of looking at POMDPs is exactly kind of along the lines of what we talked about with belief states corresponding to evidence. And that is, I'm not actually in state S. I don't know what state I'm in, but I do know what evidence I have. In other words, I know what belief state I'm in. And so I can take actions, but then after I take an action, instead of being told, hey, we're in state 5 now, what comes back to me is not a state, but an observation. Okay, I went left. I'm sensing a wall. I don't know what state I'm in, but I'm sensing a wall. And so now it's up to us to track that information about the uncertainty over the states. POMDPs are actually just MDPs over belief states, which are distributions over states. But in practice for us, what that's going to mean is you can start to think about the state not being what's actually happening in the world, but being what you know. And when I take an action and an observation comes in, I know a little more. And I can do computation over the state given what I've observed. We're not going to get fully into this today. This is just our first slice at this. And the reason I'm going to do this this first slice at it is to conclude this lecture with the case I promised at the beginning, which is how we think about the Ghostbusters game, where my actions include bust here, bust here, bust here, bust here, or also take a sensing action. Right? A sensing action doesn't end the game. What it does is it gathers an observation and puts me in a new state where, again, I can choose to sense more, or I can choose to take a busting action. So in static Ghostbusters, we have a belief state, which is a distribution over actual states, which is determined by evidence to date. What's my belief state? It's my distribution over ghost location. That is a function of all the sensor readings. So I could either talk about, my state is this vector of probabilities. I can do that. Or I can say my state is these 6 sensor readings, from which I can compute the distribution over ghost locations if I want. Okay, so I have a belief state which is determined by my evidence to date. I can think of there being a tree over evidence sets. I have a certain amount of evidence, initially none. I take some actions. Some of those actions are sensing actions. When I take a sensing action, what comes back is more evidence. Right? In sensing, I pick what variable you're going to reveal, and then what comes back is the evidence, the actual value of that variable. Now, when I compute expectimax in these trees, I'm going to need to do Bayes-Net-style computation to say, okay, given these 7 sensors I've already done, if I go to the upper right corner and reveal that, what's going to happen? And the answer is red, yellow, green. But what are the probabilities, given what I already know? I'm going to have to do computation in that Bayes-Net that we showed. Okay, so how are we going to solve POMDPs? There's a whole general issue of solving POMDPs. They're hard. POMDPs are really hard. Remember I always say this is AI, everything here is NP hard? POMDPs aren't. They're P-space hard. This is a lot worse. It's a lot worse. Instead of corresponding to like logical formulas, this is formulas with quantifiers. Okay, it's a lot worse. So, however, one way to solve POMDPs is to use expectimax over these evidence-specified belief states. So I can think, all right, I'm in the state where I know nothing, and I can do the following things. I can bust, great, or I can sense here, sense here, sense here. If I sense here, what's going to happen? Red, yellow, green. With what probability? I can compute it with Bayes-Nets. Okay, let's say it's green. I'll be in this state. I have all the evidence I had before, plus 7, 3 is green. I can bust or I can sense more. And I could build out this whole tree. This is exponential. Eventually I'm going to have to truncate this thing. But I can solve that running lots and lots of Bayes-Net inference over this tree. And that will let me solve this POMDP, or at least approximate a solution to it. So, let's do that. Let's talk about, let's go to here. All right. What are you seeing now? It's the exact same Ghostbusters. We are in the belief state shown here, flat distribution. You can think of it as a vector. Our state is a big vector of real numbers. Or you can think of it as we're in the empty set. The evidence we have is the empty set of evidence. And so what's going to happen, I'm not going to click a square anymore. I'm just going to hit go, and a computation is going to happen. It's going to be a value of information computation. It's also going to be a search in this POMDP tree. It's the same thing. And what's going to happen is the system is going to compute which variable should I reveal, or alternately I can just bust, and it's going to compute what is the highest value of information versus the actual utilities. Let's see what it does. Okay, so it decided to sense right there. And it got some value, and I'm in a new state now. I'm in the state where I know something. I know that 1, 1 is yellow, which also corresponds to this vector of probabilities shown here. I'm going to click again, and it's going to either decide to bust, or it's going to decide to sense again. What is that computation? That computation is, well, here's my MEU if I bust, here's my MEU if I sense and then bust. That's a value of information computation, the difference between acting now or revealing a variable and then acting. Okay, that's value of information. Let's see what it does. Okay, it decided to sense. Let's go again. It's going to sense. Let's go again. I think it's going to sense again. It's going to sense. Now we get to this point where I could bust, or I could take the cost of another sensor reading and sense again. What's best? Well, that's a VPI computation. It's going to do it. And it senses. It senses again. Sense. It's very cheap to sense here, so it's being extra cautious here. All right. It decided to bust and it hit. So what you can see here is you can see now that this action selection is not just a computation of where is the ghost, but how much uncertainty do I have? How much will that uncertainty on average be reduced? Notice it actually went up sometimes when I got confusing evidence. On average, how much will it be reduced by a sensing action? How much more valuable is that in terms of ultimate utility? What should I do? This is a POMDP agent running expect-a-max over belief states in order to do Ghostbusters. Starting next time, we're going to look at an even more fancy version of Ghostbusters where the ghosts actually move around. That's going to be the basis of your next project. Okay, so we'll talk about tracking invisible ghosts instead of just sensing them and trying to catch them. We'll do that next time.